Hello everyone. We use regression analysis when our explanatory variables are continuous. We use ANOVA when our explanatory variables are categorical. What can we do when we have categorical explanatory variables and also measure other continuous variables which are not our response variable of interest but could affect the response variable? These are the aims of this lecture. Let's start with an example. We want to evaluate the effect of three types of diets on the weights of pigs. The experiment will be conducted on 15 piglets. Prior to the experiment, these piglets have the same diet. During the experiment, each type of diet is assigned to 5 random piglets until they reach adulthood. These piglets are not uniform in size, so their weights before the experiment are not the same. Do you see a potential problem with this experiment? The piglet weights are likely to affect pig weight. A larger piglet are likely to grow into a larger pig and vice versa. Therefore, the effect of diets on pig weight could be confounded by the piglet weights. So what can we do? We have several options. Option 1, we can increase the number of piglets to make sure all treatments are randomly tested across the full range of piglet sizes. However, this option is impractical as we only have 15 piglets. Option 2, we can group the piglets based on their weights and assign the treatments within each group. This option works if we can categorize the piglet weight into meaningful and distinct groups, for example, small, medium, and large. However, the piglet weights are likely to be continuous and difficult to categorize. Option 3, we can analyze the differences between pig and piglet weights. Using this option, we compare the weight gain and not the weight per se. The response variable of interest in this experiment is the pig weight, not the weight gain. Option 4, we can adjust the pig weight by the piglet weight. This is known as the analysis of covariance or ANCOVA, and the piglet weight is the covariate. A covariate, usually denoted X, is a continuous variable measured on the same experimental unit as the response variable. We use covariate to adjust the treatment means. The treatment means are adjusted to what its estimate would have been if all treatments have the same value of X. In previous example, pig weights are adjusted by the piglet weights. So we use the adjusted mean to compare the treatments. Adjusting the mean will increase the precision of treatment comparison. Inclusion of covariate in ANCOVA model often causes a difference in the decision for accepting or rejecting the null hypothesis. ANCOVA can be used as an alternative to blocking when blocking is not possible, or can also be used in addition to blocking. In addition to the usual assumption of ANOVA, ANCOVA has two additional assumptions. In our example, the weight of piglets are not affected by the type of diets, as these piglets are on the same diet prior to the start of the experiment. If this assumption is not true, the ANCOVA can still be done, but the interpretation is different. ANCOVA is a combination of a linear regression and an ANOVA. The linear regression provides adjustment of the response variable y based on the covariate x, while the ANOVA provides the comparisons among treatments based on the means of this adjusted y. The linear model We can use CRD, RCBD, Latin square, and any blocking designs with ANCOVA. We can also use ANCOVA with any treatment designs, such as factorial or split plot designs. The ANCOVA table for CRD the ANCOVA table for RCBD, note that the degree of freedom for a covariate is always 1. Let's see an example. How can we analyze this data? This is a CRD experiment. The number of treatment is 3, and the number of replication is 5. The response variable is yield. The covariate is the yield from previous year. First, we need to reformat the data for analysis. We have 3 options to analyze this data. The first option, we can use ANOVA. We use ANOVA when we are interested in comparing the mean yield among treatments, and we assume that the yield variation among plots before treatments are negligible. Based on the interval plot, the difference in treatment means might not be significant because the variation within treatment is large. The skeleton ANOVA Based on this ANOVA result, there is no significant treatment effects at the 5% significant level. The second option, we can use regression analysis. We conduct a regression analysis when we are interested in the relationship in yield before and after treatments. Based on the scatter plot, there is a linear relationship between current yield and the previous yield. The regression equation is where there is a significant slope at the 5% significance level. The third option, we can use ANCOVA. We use ANCOVA when we are interested in comparing the mean yield among treatments, but we know there are large variability among plot yield before treatments. Based on the regression equation, we can calculate the fitted value for each plot. This fitted value is the adjusted yield. We can generate an interval plot for this adjusted yield. Once we adjusted the current yield using the previous year yield, there seems a significant difference in treatment mean. The ANCOVA table now, there is a significant treatment effects at the 5% significant level. Do you notice how these three analyses partition the total sum of squares? ANOVA, regression, ANCOVA, when we fail to account for the covariate, the sum of square of this covariate is added to the residual sum of square. The treatment sum of square is also underestimated as the difference among treatment means are masked by the differences in the covariates. ANOVA, regression, and ANCOVA are all based on a linear additive model. If we can build the model, we can analyze the data. Skeleton ANOVA will help us in building the model. Now, can you do this?